All right. We started last time in section 9.4, and we were looking at counting techniques. And there are several counting techniques. Let me run through them pretty quickly because we're going to have to be making decisions about when to use what. So our first counting technique was the fundamental principle of counting. And these problems end up looking like different things happening in multiple steps. So, and I gave an example. Our example in the work was about Pizza Planet. But I gave an example of getting dressed in the morning, right? You have to pick a shirt, you have to pick a pair of pants, and all the different components that you have. You can't pick two of one and nothing of the other in some of these situations, like clothing would be that way. And so we're looking at a fundamental principle of counting. Permutation of like objects. So that happens when we're trying to count the number of ways something can happen, but some of our objects are identical. And they can be identical in a variety of ways. Like maybe they truly are identical. If they're truly identical, like my package of Starburst, that's one option. But it might be that just the category descriptions are identical. For example, it's the make of the car. Or maybe it's the nationality of the swimmer, like in the Olympics, right? How many golds and silvers and so forth for different, athletes. So it could just be one component that we're isolating and calling people the same in, even though obviously the people themselves are different. That kind of thing can happen. The next one we talked about was a permutation of unlike objects. So in this scenario, we have objects that don't actually have things in common, or we're looking at them as unique completely. So we can't use the Starburst example here at all because like the pink Starbursts are exactly the same. But our people example works pretty well. So if our individual people are different, those would be a permutation or a combination, which we're about to do in a second. The difference between permutations and combinations is whether or not the order matters. So when we do a permutation, the order matters, and our example was winning a raffle, but the categories that you win in or the prizes that you win are different, right? So if the prizes are different, then it matters which order you were selected in. And then the combination was if the prizes don't matter, if you're getting the exact same grouping regardless, then it doesn't really make any difference if you were selected first, second, or third, and that would be a combination. So we have different formulas for each one of these, but the biggest issue usually is trying to figure out which one to use. If you can figure out which one to use, students are usually highly successful in computing everything they need to compute. But we have to make sure we can figure out which one we're using. So we're going to do some examples where we have to decide along the way, which type is this? All right, so example number 6. Example number 6. We have phone numbers. So we have the phone numbers in a large business. The phone numbers all start out 405767. And then there's 4 digits at the end, okay? It says how many different phone numbers are possible. So we have 4 different ways of thinking about counting strategies. Which one does this one seem like it should be? It is. It's the fundamental principle of counting. Each of these numbers selected don't overlap with any others, just like your shirt does not overlap with your pants in terms of making a selection if we ignore, like matching, right? Okay, sorry. Yeah. All right, it is. It's a fundamental principle of counting. So there are 4 different numbers that we have to pick. How many numbers do we have to pick from? 10. What are they? 0 through 9. So don't forget about 0. That's a common mistake. Yeah, there are 10 different single-digit numbers, 0 through 9. And I can have any of those 10 digits in any of the 4 places, right? So what is 10 times 10 times 10 times 10? It is 10,000. So this company could have 10,000 different numbers. Most of what we're going to be doing are word problems with context, so we make sure we put units on the end. There's 10,000 different numbers. Does it make sense? Yeah.
So, whenever I first looked at this, I was thinking it was more like the 4 factorial.
Mm-hmm.
So, what's the difference between those two?
So, if we had a condition on this one that said something like the digits can't repeat, it would be more like a factorial. But I could have all 4 of the last digits all matching, right? And so because I can repeat the digits, that's why the 10s all show up as 10s. But there are cases where I can't repeat things, and then I would have factorial kind of notation going on. Yeah. And occasionally there's more than one way to do a problem. And so let's take a look at 7. I can't remember, well, Seven's an example. There are 2 ways to do number 7, and they both work out beautifully. So a worship team practices 8 songs on a Wednesday night for the Sunday service. If the worship minister plans to choose only 5 of the 8 songs practiced, in how many ways could the songs occur? What strategy do you think?
Permutations of unlike objects.
Okay, so permutations of unlike objects, that is one option. There's another way that we could do it too. Anybody see another option? It's not a combination. The order does matter, right? Because it asks at the end in how many ways could the songs occur. So a different ordering is a different count in this. So it's not combination.
Is it a permutation of like objects since they're all songs?
It's not permutation like objects because they're all songs. Because again, we're trying to distinguish. Because otherwise, then there would be no discernible way to tell the difference at all. It's not that one, which means I'm down to. Yeah, it can be the fundamental principle of counting. So this one with the fundamental principle of counting starts to mirror what you were talking about with the last one. So let's do permutation of unlike objects first, and then I'll show you what it looks like if you think about it as a fundamental principle. So permutation of unlike objects, I have 8 objects I'm choosing from. Whoops. And I'm choosing 5 of them. Right? And the formula we encountered last time meant that I put 8 factorial on top. And then what goes on bottom is how many I don't choose. So over here, right? Let me get it over here. On the bottom, it's n minus r. So if I'm choosing r, then n minus r would be the number I don't choose. The number of people that don't win, the number of songs that aren't sung, whatever. Or if you don't like thinking about it that way, you can definitely think about it very much like a formula perspective. That's what I was going to say, where it's 8 minus 5. And that's fine too. Either way, we have 8 factorial on top and 3 factorial on bottom. Now, we talked about this last time. We could literally write out all the 8 down, 8 down to 1, 3 down to 1. But we can also shortcut it and just write down 8, 7, 6, 5, 4, and then stop at the 3 factorial. If it matches identical to the bottom, it can cancel. And the reason it can is because I would write out 3 times 2 times 1, 3 times 2 times 1, the 3, the 2, the 1, they'd all cancel out. So I'm left with multiplying 8 times 7 times 6 times 5 times 4. And what is 8 times 7 times 6 times 5 times 4? So there are 6,720 different arrangements, or some variation of that word. Okay, so this is also a fundamental principle of counting. So on this one, if you think of it as a fundamental principle of counting, there are 5 songs I get to pick, so there's 5 choices I get to make. But unlike the last one, I don't repeat things. Right? Once I've chosen the song, I need to choose another song that's different. So I choose from among 8 songs the first time, but then my second song choice means I choose from among 7, and the next one from among 6, my 5, and my 4. And you'll notice that those numbers are exactly the same numbers that showed up in the numerator after we reduced it with the 3 factorial in the denominator. There's not a right or a wrong. They're both correct, and they're both correct ways of thinking about it completely. All right.
Usually have them on those 2 kinds of columns, like permutation and fundamental. Do they usually go back and forth?
It depends on the problem. For example, this one over here was fundamental principle of counting, and there's no way that this is a permutation of unlike objects. It doesn't work that way at all. But if something is a permutation of unlike objects, it actually usually does have the ability to be done with the fundamental principle of counting. That may or may not be how you think of it, but it usually does. Yeah. All right. Next example, card decks. Have we talked about card decks in here?
Yeah.
I thought so. I went through a whole scenario of like blacks and reds and kings and queens and all that stuff, right? Okay, good. All right, so we're starting this one with a game, and we start with a standard 52 card deck. And the first question that we're simply asked is how many different hands of cards can you deal? Okay, so what kind of a problem do you suppose this might be?
Combination?
It is a combination. Why a combination?
Because the order doesn't matter.
Yeah. So in card games, what's the first thing you tend to do when somebody hands you a whole handful of cards? Put them in some kind of an order if you're given the hand, right? Depending on the game will depend on the order. Maybe you're matching numbers, maybe you're matching suits or letters is not what I meant to say. Suits or certain, like strings of numbers and, like 1, 2, 3, 4 kind of thing. I mean, it depends on the game, right? So any kind of card game, typically the first thing you do is you reorganize the cards. So the order of them does not matter, how they were dealt to you. It only matters what the order is when you're looking at the end for your game. So yeah, it's a combination. The order doesn't matter. So I have a combination. I have 52 cards I'm choosing from, and I'm going to make a 5-card hand. Okay? With the combination, I put that same 52 factorial on top, just like in the factorial or in the permutation one on the last problem. But my denominator includes not only the number of cards that aren't chosen, but the number of cards that are. So the number of cards that I choose is 5 factorial. How many cards do I not choose? 47, right? And it's just the 52 minus the 5. And you can do a real quick visual check. These two should add up to the numerator in a combination. They always will, okay? And they do. 47 and 5 is 52, right? Okay, cool. So we're going to write out the factorials until I get to the biggest one that it matches with on bottom, so 47. So I have 52, 51, 50, 49, 48, and 47 factorial. So I have the same 47 factorial, and then I have 5, 4, 3, 2, and 1. Okay, 52 factorial is too big. Your calculator cannot tolerate it. I mean, it will try to turn something into scientific notation. If you get things that are even too large, it might even comp out completely and tell you something like error or something, or memory overflow, depending on the kind of calculator you're working with. So the bigger the number that's got a factorial with it, the more necessary it is that you reduce it. And this one's big enough that you're not going to be able to work with it in your calculator. So we really do need to cancel out the 47 factorial parts. After you get that done, if you wanted to multiply everything on the top together, multiply everything on the bottom together and do the division, you could do that. It wouldn't hurt anything. But it's also true that everything in the denominator will cancel with something in the numerator. So that's what I usually tend to do myself because the numbers stay a little bit smaller. So for example, this 5 will divide into what? 50, and I'm left with a 10. How about the 4? 48. So what is 48 divided by 4? 12. How about the 3? The 3 will go into the 12 too, if you wish. It'll also go into the 51 if you want to. So either way, it goes into 12, since that's the one you mentioned. We'll do that one. So that would be a 4 now, right? And the 2? It could go into 52, or it could go into the 4, right? 52 is what you mentioned, so we'll go with 52. What is 52 divided by 2? 26. Okay, so the being careful part every time on here is making sure that every piece that's still present in the numerator gets multiplied. So 26 and a 51, a 10 and a 49, and a 4. So those 5 numbers need to be multiplied. And what will you get? It's a big number. Bigger than that. You might have missed one of the numbers. Yeah, you missed one. It'll do it. Did you get it, Laura?
2,598,960.
That would be it. That is a large number, right? 2 million, about 2,600,000. So this is the number of hands of cards. So this is the reason why when my dad stacked my hand one time when I went out to use the restroom, like when we were playing a game or whatever, and I came back in, I knew that something was wrong. There's no way you get the entire hand of spades when you're playing spades. It doesn't work like that, right? It's like never going to happen. Yeah, because there's this many hands of cards. That's crazy. 2.6 million hands of cards. Okay, so what we're going to do in the last two problems on this example, the two parts of this example, are examining if I narrow down what I want my hand to end up being, how many of those hands are there? So the first deviation of this one wants us to have a hand that's all diamonds, okay, just diamonds. So I'm still selecting 5 cards, but I'm selecting only diamonds. So how many diamonds are there? How many? 13 is right, yeah. There are 13 diamonds. So they're still combinations, still doesn't matter what order they show up in my hand. I just want them to all be diamonds. So from the 13 diamonds, I want 5 that are all diamonds. So this is going to be the number of hands that could be dealt that are all diamonds. So we're going to take 13 factorial. And what's the denominator going to be? Okay, so 8 factorial and 5 factorial. 8 and 5 do add up to 13, so that's sort of a mental check. We're going to write the 13 out till I get to 8. 13, 12, 11, 10, 9, and 8 factorial. And then 5, 4, 3, 2, and 1.
You said that you don't have to write the 1, right?
You don't have to. It wouldn't hurt anything. Yeah, if you left it off, it doesn't matter because it won't change the value. Yeah. Okay, the 8 factorials went away. This one actually works really nicely to pair the numbers up on bottom if you wish. Right, so like 5 times 2 is 10. And the 5 and the 2 have a 10 to mark off the numerator with. 4 times 3 is 12. And that's in the numerator as well. So for this one, what I'm left with is a 13, an 11, and a 9. So what is 13 times 11 times 9?
1,287.
1,287, which you probably would have told me before was a big number. But when you compare it to our 2 million number, it is not a big number. I mean, 1,200 hands of cards is a lot of hand of cards, but not when compared to 2,600,000, right? It's just not. So there is a very unlikely chance that you're going to get all diamonds. Okay? All diamonds is called a flush, by the way, when you're playing poker. All right, so the next one is going to say, what is the probability of getting, hang on. Oh, probability. Yeah, there we go. What is the probability then of getting that 5-card hand? Okay, so this one over here told me the number of 5-card hands. This told me the total number of hands at all, right? All that exist. And now I'm going to find probability. So probability is found by taking, so this is the probability of having 5 diamonds. So this would be the number of hands that have 5 diamonds, divided by the number of all 5-card hands. And that's the previous problem, two parts of our problem that we just did. So our 1287 goes on top, and our 2,598,960 on bottom. And then if we multiply by 100, we would actually get a percentage. We're not asked to do that here, but we do that often. We think about it that way. So if you do the division, we're going to report our answer to 4 decimals on this one. What do you get? Yep, And if you multiplied that by 100, I won't on my screen, but Kenzie, if you multiply that by 100, what does that give you? 0.05%, which is not 5%, right? 0.05% is very, very small. If your grade in the class were off by 0.05%, you would be just like, seriously, you're not going to give me that letter grade, right? Like, it's that close. It's so close, right? It's a very, very small number. The hand of all diamonds is rare, right? It really is very, very rare. That's what that's telling you. All right, so let's take a look at another example. Our last one today, it's committee. We have a committee of 3 people that we are selecting at random from among 7 seniors, 5 juniors, and 3 sophomores. Okay? And the first one wants to know the probability the committee consists of all seniors. So this problem kind of does what the last problem did, part C, without doing the A and B to lead up to it. Okay, in order to find a probability, you need to know the number of ways your outcome can happen that you want, whatever the desired outcome is, and you need to know the number of ways anything can happen. So anytime the question is posed like this, you have to do the part A and the part B from the previous problem in order to do the part C that your question's asking. So when I look at this problem and it asks about the probability of all seniors, I'm thinking about it like this. The probability of, and it's 3 seniors, will be the number of ways that I get 3 seniors divided by the number of ways I get any 3 of my students. Does that make sense? All right, I'm combining the 2 pieces together. The number of ways I get all the seniors, the number of ways I get, well, anybody. So what I really have to find is I have to find the numerator. I'll call it part, actually I've got these labeled A and B, so let's call this number 1. And the denominator, and I'll call it number 2. And once I find those quantities, I can divide them and be done with the problem. So we'll do number 1. The number of ways of getting all seniors. Well, how many seniors are there? 7. And how many people am I choosing? 3. Now, I didn't stop and ask you, but does it make sense that this should be a combination? Yeah, when you have a committee, it doesn't matter if you were put on the committee as the first person or the last person, you're still on the committee. So committees don't have an order mattering situation. Okay? So I have 7C3. So I have 7 factorial on top. What goes on the bottom of 7C3? Yep, 7 minus 3, which is 4, and 3. So the 3 shows up down there, and 7 minus 3, which is 4, shows up. So this is 7, 6, 5, and 4 factorial over 4 factorial, and then 3, 2, and 1. Okay, so 4 factorial cancels. What else? 3 times 2 cancels with 6. So all I'm left with is the 5 and the 7, and 5 times 7 would be 35. Okay, so I found the numerator. It's 35. Okay, we need to do the denominator now. So number 2, I need to find the number of ways I get any 3 people. So, how many people are there? Somebody said it. 15. Yeah, there are 15 people. So I would add up the seniors, juniors, and sophomores. So I had 7, 5, and 3. That is 15. And how many am I choosing? 3. So 3 factorial will be in the denominator. How many am I not choosing? 12. 15 minus 3 are 12. So the 12 factorial goes in the denominator as well. So I have 15, 14, 13, and 12 factorial over that same 12 factorial, and then 3, 2, and 1. 12s cancel. How about the 3 and the 15 make 5, right? 2 and 14 give me 7. So I have 5, 7, and 13. What is that? 455. So again, back up here, I've got 455 now. Now, I don't have to put it in a decimal form. Fractions are fine, but I do need to reduce the fraction. What do these both divide by? At least 5, right? So if I divide each of them by 5, I've got 7 on top. What's 455 divided by 5? What is it? 91. Does 7 divide by 9? 91 divide by 7? Did we check?
Yeah.
I think it did actually, yeah. So if I divide by 7 here, this is 1 out of 13. So you can leave in fraction form 1 out of 13. If you wanted to put it in decimal form from any version of this, you could, and that would be okay too. 4 decimals again. So if we took either the 1 out of 13 or the original 35 out of 455, what is it in decimal form? Yeah, 4 decimals. We'll go with 4. Yeah, so it's approximately 0.0769. So either of those versions, the answer would be acceptable. Now, we talked about complements before, right? So the complement of all seniors is not no seniors. And that's actually what my next question says. It says no seniors, but these are not complements. The complement of all seniors actually means I just have somebody on there who's not, right? I have at least one non-senior person. So I don't want you to think, oh, look, I don't have to do a lot of work for this one. I mean, you don't have to do as much as Part A, but you can't just do 1 minus it either, which you might be inclined to think you could. It doesn't work like that. When it has no seniors, what it's really saying is that it needs all juniors and sophomores, right? So what I want is I want the probability of having all, or you could put 3, juniors and sophomores on my committee. And to do that, much like last time, it means I need the number of ways of having all juniors and sophomores compared to the number of ways of having any 3. But we already know one of those. Yeah, the denominator is still 455. It didn't change. I have the same group of 15 students. This denominator I already know, which is why the problem is easier than Part A, because I've already done part of it. However, I do need to get the number of ways of getting all juniors and sophomores. So how many juniors and sophomores are there?
8.
There are 8. And how many am I choosing? 3. So I have 8 factorial, and I have the 3 factorial. What else do I have in the denominator? 5. Yeah, 8 minus 3, which is 5. So we'll multiply 8, 7, 6, and then there's that 5 factorial. And then I have the 3, 2, and 1. Okay, so the 5 factorials cancel. What else? 3 times 2 is 6. So what is 8 times 7? 56. So 56 on top, 455 on bottom. It will reduce. I'll just spare you the trying to figure it out right now, but they both divide at least by 7. So what is 56 divided by 7?
8.
8, yeah. And what is 455 divided by 7?
65.
65. So this would be stopped in terms of a simplified fraction at this point because the top is even, but the bottom is not, and there's nothing else that will divide the 8. So you could stop here. If you wanted it in decimal form, you're going to go with 4 decimals. What's the decimal form value for this? Approximately, of course.
1, 2, 3, 1.
Yep. And that's perfectly acceptable for a probability value as well. Okay,